Hello there and welcome to the series of videos going through the content of A-Level Further Maths. Here we're looking at matrix transformations and more specifically the enlargement and stretches type of transformations, so we can answer questions from exercise 7c. So here we're going to be looking at what happens when we've got these types of matrix here, 3, 0, 0, 2. What type of transformation is that? How is it going to affect coordinates, etc, etc. So we've got a few questions here lined up for this matrix here. So find the image of T prime of the triangle T with vertices. Okay, so these are the original vertices and we need to find the image vertices on this triangle here. So the way we do that is we set up a matrix with all of the coordinates put in their columns, just like we have here, and the transformation matrix will be at the front. So let's see what happens to each of these coordinates. We're multiplying along and down, until we get 3, 2, 3, 4, and 6, 4. Okay, so these are the set of coordinates then. The set of coordinates are 3, 2, 3, 4, and 6, 4. Part B here is to sketch both of the sets of coordinates on a same grid. We can see what's happened here. So the original triangle was a one dimension by another one dimension triangle, and in this case here the x dimension is now a distance of 3 along and the y dimension is now a distance of 2 upwards. And I suppose this kind of makes sense when we look back at the matrix that we used to transform that triangle. The x-axis here in the x position has been stretched by a scale factor of 3, and the y-axis in the y position has been stretched by a scale factor of 2. So that's what happens in these sorts of matrices here, where there's a 0 and the 0 in the other diagonal. Where there are two numbers in the leading diagonal, that's the axis stretching scale factor for each of the x and the y-axis separately. If the numbers were equal, then it would be an equal stretching scale factor in both axes dimensions. In this case here it's 3 in the x, 2 in the y. So finishing off this question here, part C looks for us to describe geometrically the transformation represented by M. So in this case here it's stretched in a scale factor 3 parallel to the x-axis and a scale factor of 2 parallel to the y-axis. So in both of these questions here, the x-axis is going to get stretched out by a factor of 3 and the y-axis is going to get stretched up by a factor of 3. So in this case here, these lines are what we call invariant lines. These lines are not going to move. Any coordinate along this line is going to get tripled. It's not going to actually move anywhere, budging from this line here. Okay, we'll move on to invariant lines in a second, but I just want to fully describe what's happened here. So the matrix A00B represents a scale factor stretch by A parallel in the x-axis and a scale factor B parallel in the y-axis. If A is equal to B, then there's just a standard scale factor stretching. So as I said, these x and y axes, when they've been stretched in their direction, the x and the y-axis are both going to be called what we call invariant lines. Now they're called invariant lines. Now what that doesn't mean is that each point on this line is invariant. It means that if we were to draw this line out and then stretch it, you would still see just a solid straight line. So each point on this line here is transformed to another point along this line here. And the same for the y-axis when we do stretching as well, in that any point on the y-axis will stay on the y-axis. And that's what it means to be an invariant line. It means for any point on that line, it is mapped to another point on that line. But that doesn't mean that these points are invariant. The only point that would be invariant under a stretching is the 0, 0 coordinate, because that point, no matter what transformation you do, will not stretch. It will stay at 0, 0, so the point 0, 0 maps to itself, whereas an invariant line is made up of points that will be mapped onto the same line. Not necessarily back to the same coordinate, but onto the same line. Okay, and the final thing we're going to look at in this video here is what the determinant has to play in a scale factor stretching type question. we saw earlier, let's just go back a few slides here, we saw earlier that the area for this triangle number 1 here is 1 times 1, the 2 dimensions, times by a half, so the area here is a half. And the area for this triangle here is base times height divided by 2, that would be 3. And if we were to work out the determinant of this matrix here, this would have a determinant of m. So determinant of 6 rather. And you can see here what has effectively happened to the areas from both of these triangles. It's been the determinant, that's 6, that when we multiply by the area for triangle T, gives us the area of triangle T prime. Okay, so the determinant can be thought of as the area stretching scale factor from one shape to another. Okay, so it's the area stretching scale factor, not the length scale factor. You find those from the different columns on your matrix. It's the area scale factor from one shape to the next. Okay, so let's get back to that question we were on. So moving across now. So if a linear transformation is represented by a matrix M, then the determinant of the matrix M represents the scale factor of the change in area. Okay, so if this value is negative, it just means the shape's been reflected, but it's still the area is still going to get a scale factor enlarged by that determinant amount. In this question here, let's take the matrix 2, 0, 0, 4. And we've got a set of coordinates on a triangle there, and we're looking to work out some areas. So for part A, it just asks for us to describe the matrix transformation. So we know here that the x-axis is going to stretch by a scale factor of 2, and the y-axis is going to stretch by a scale factor of 4. And that's just quite easy to read off the diagram. Part B, the triangle T has vertices of these 3. Find the area of the triangle. Let's just do a little sketch just to visualize the problem here. 1, 0, 4, 0, 4, 2 above. And remember, area of triangle is base times height divided by 2. So 3 times 2 divided by 2, we get 3 units squared. For part C, triangle T has been transformed using matrix M. Find the area of the image of T. So if it's been transformed under the matrix M and we're looking to find the area, we can use this piece of information up here, this cheeky shortcut up here, to work out the determinant of this matrix here, and then just times it by the area of the previous triangle before we've transformed. So the long way of doing this question would be to transform all of these coordinates under this matrix here, draw yourself a diagram and work out the area on that diagram. Or you can just use the cheeky shortcut, which is to work out that the determinant of this matrix here is 8. So the area is going to get scale factor enlarged by a factor of 8. So the area of the new triangle is going to be 24 square units. 3 times 8 giving you 24. 3 from the original area, 8 from the matrix determinant, 24 is going to be the area of the new set of coordinates once these have been transformed under M. Okay, so your turn to have a go at this question here then. It's to do with invariant points. Okay, so pause the video and try this one out. Okay, so let's have a go at this question 3 here then. So quite a difficult question, not really the type of question that we've seen earlier in this video, but let's have a go at it anyway. The unit square is transformed using the matrix 3, 0, 0, 4. Now, the unit matrix, the unit square must be the set of coordinates 0, 0, 1, 0, 1, 1, and 0, 1. If you want to pause the video and have a go at this question again, then please feel free to do so. I'm going to carry on. So if we plot these 4 coordinates on a grid, we're going to get this set of 4 coordinates here. It's called the unit square because it's a square with a distance of 1 on all of the sides of this square. Now, write down the coordinates of any invariant points. So originally the unit square is transformed using this matrix. Now we know from this matrix here that when matrices look like this, it's the x-axis that's been stretched by a scale factor 3, and it's the y-axis that's been stretched by a scale factor 4. So let's go ahead and draw that. So the x-axis by a factor of 3, so this is now at 3, 0. The y-axis by a factor of 4, so this is now going to be at 0, 4. 0, 0 doesn't move because you're stretching a 0, so that doesn't really matter. And the 1, 1 coordinate is now going to be stretched to 3, 4. So it's now a rectangle that looks like this. And for part A, the question is, write down the coordinates of any invariant points. Now an invariant point is a point that doesn't move when it's been transformed. This 0, 0 coordinate here is the only invariant point on this question here. And generally that's going to be true of a lot of different questions as well. Write down the area of the resulting rectangle. Well, I could do this in 2 ways, couldn't I? I could quickly see the base here is 3 and the height here is 4, so I know my area is 12. Alternatively, area equals 12. Alternatively, I could look at the determinant here and times it by the area of this, which is 12, times by 1, so that's 12 as well. So yeah, either way your answer is 12. And if you've got no units, I'd just write 12 units squared there. Alright then, thanks for watching this video here. Have a go at some other questions from exercise 7C to see how we've got on the other topics here. Okay, so persevere through those difficult ones and ask your teacher for help if you need any. Thanks for watching.